So in this lecture, we will talk about 3D steady potential flow. Before we do that, let's go ahead and review what we did last time, very quick. Um, so in a 3D steady potential flow, we know the following. We know that what we have been trying to do is we want to take this with the velocity. There is a possibility of expressing the velocity in terms of the gradient of a scalar. Okay, and this really comes from the fact from continuity, because we said that this has to be zero. Okay, and the direct consequence of this will be this is equal to zero. In other words, this gives you lambda squared times phi is zero. And we call this the Laplace's equation. So this is very good, but that means that whatever potential flow they use, whatever approximation for the scalar, has to be such that it satisfies this. And if it satisfies the Laplace equation, then it means that it satisfies continuity. Okay? The other thing is, if there is a potential flow, okay, if the flow is potential, then it is irrotational. So we cannot have a potential flow for rotational flows. Okay, so if it's irrotational, that means that the condition for irrotationality is that this is equal to zero. Then from here, the gradient cross product, the gradient of phi has to be zero. Okay. Now, if we go to Bernoulli, okay, now the equation from Bernoulli, we know that it says that P plus 1/2 rho V squared is going to equal to P infinite plus 1/2 V infinite squared. Remember, Z is actually going to equal to Z infinite, so we can cancel that out. So if I bring the pressures on one side and take the velocities at the other side, we can further express this side as 1/2 rho V infinite squared, and that will give you 1 minus V infinite squared. Okay, now I could divide both sides by this quantity, by the dynamic pressure, and that would give you P minus P infinite divided by 1/2 rho V infinite, and that's the same as 1 minus V infinite squared. This quantity is called the pressure coefficient. Okay? And to understand the importance of pressure coefficient, we will learn that later. But basically, the pressure coefficient of a typical airfoil at the 40% span, as for an example, it looks something like this. And you can see that these are the test data. Okay, this is actually experimentally calculated. And these are the approximations that we do by numerically. And they're pretty good. Okay, So this is the pressure coefficient at the upper surface and the bottom surface. And that will be different because although this is the same, but your pressure at the top and the bottom will be different, okay? So if I have the airfoil, okay, what I'm saying is in the airfoil, you're gonna have a pressure at the upper surface. That's gonna be a consequence because I have a pressure at the upper surface. I'm going to have a pressure at my lower surface, and that's a consequence because I'm going to have a pressure at the lower surface. Okay, and this is what the pressure coefficient actually looks like. The one that's actually experienced by the flow. Okay, and this particular plot. It was done at 40.9% of the span. When we talk about the span, you got the aircraft, right? So the aircraft, this is the total span of the aircraft. When he's saying this is B. So he's saying that this is approximately calculated there. Okay, it's at this distance about 0.41, 0.41 B. This is total B from tip to the tip. Okay, so this is how this was calculated. Okay, so uh, given that, the also just a quick review, the conservation of mass gives, we know the conservation of mass is the following equation. Okay. Now, if I have the potential, right, and I know that I am assuming that this is constant along the streamline, then we know that this term is equal to 0, right? And is equal to 0. So the only term that's left in this equation then is this equation, okay? But if you recall, I also set that to be 0 because we defined that if I have a velocity potential, right, this equation has to be 0. So in other words, this is actually going to give me rho. Rho can cancel out because this is a 0. It says that this has to be 0, okay? So this term is actually 0. As a consequence of that is the following. So we know in the Cartesian coordinates, as for an example, this is given by this equation. We have done this several times. Also in the stream functions, we show that this was equal to partial of psi respect to y plus partial of y minus partial of psi respect to x. Okay? That's just a direct consequence of saying this is actually equal to 0. Now, if I just take this, now note that this is what I could do in this problem. I can say this particular equation is nothing else than there's a consequence of the gradient of two streamlines. Okay, this has to be 0. And this is from a vector identity that you can show that the gradient of the cross product of two scalars is actually going to be 0. Okay, this is going to be 0. This is from vector calculus. So therefore, this has to be 0. So now, if we compare this equation, right, with this equation, that this is 0, you can conclude that your V, right, we define V as the potential, but the potential can be found by the cross product of two streams. Okay, and we say that that this has to be a constant value as well. Why it has to be constant? Because this is a gradient. So if I integrate on both sides, you will be able to show that you get a value of a constant. Okay, so there are a couple of nice nice applications to this. Let's see some of them. So let's see what happens to, let's consider a uniform axial flow in cylindrical coordinates. So in this case, just note that my polar coordinate, I'm calling this phi, and this angle I'm calling it theta. I'm going in the direction y. Okay, it's not in terms of z. So in this particular case, what we can see is that the uniform flow that I have is only coming in one direction. So the uniform flow in is in x direction, and that gives you u of x, gives you u infinite, u of r is 0, and u of phi is 0. Remember, I'm using phi instead of theta, okay? Then later we will put everything in the coordinate system that we are used to. So we want to find here, what is this? And what you know is, what's given in the problem is that your psi1 is equal to psi, and your psi2 is equal to phi. Okay, it's the angle. So given that streamlines, so in the polar coordinate system, you can express your velocity potential as follows. Partial of phi respect to r is equal to minus 1 over r partial of psi respect to x, and u of x is equal to partial of phi respect to x is equal to 1 over r partial of psi respect to r. Okay, so if that is given, this is what we know. This is a definition that you just learned, right? For the polar coordinate system. So if this is true, now what we could do is the following. We can have various cases. So I could go ahead and say, let's consider partial of psi, partial of phi has to equal to u of x. Okay, that's your stream velocity. And so we know that phi is actually going to equal to your stream velocity. So I integrate on both sides now. And I'm going to have a constant. Okay, let's call this constant in r. Now, I also know from the problem that u respect to r was equal to ur, and that was 0. So from here, I can see that this is actually equal to a constant in x. Okay, so when I compare these two equations, right, it has to be a function of r and a function of r and x and a function of x alone. When I compare these, I can say, oh, you know one thing? It looks like my function then is actually equal to u of x, because this seems like to be this function. And then I just need a function of r, then that's what's missing there. However, since I have no information for my r, I have no information what's going to happen with this function and nowhere to be found, right? I can set that value to whatever value I want to know. So one way I could do is I can say, let me go ahead and set this value equal to 0. In such a case, what I will have is I will have I will have a potential in x. Okay, so this is the first thing. So I found what my potential, I found what the value of my potential is. Now I need to find this, what my psi is. So to find my psi, I will go to my next equation that says partial of psi respect to r is going to give me u of x is equal to u of this. This is going to come from the fact that I know that this equation right here, okay, these are the equations I'm using. Okay, I use these two equations here to find my ux, my ur. Now I'm using the same equations, but to find my psi. Okay, so I do this, and I can find that psi of x is actually equal to u. This is r, so I can multiply r on both sides. So that means if I integrate on both sides, that would give me u infinite r squared over 2 plus a function in x which I do not know. Now I go to the next equation. From this equation, right, this is equal to 0 now. So that equation tells me 1 over r is psi of d of x is equal to 0. Okay, from here, the psi of x is 0. So from here, I find that psi is actually equal to a constant f of r. Now, if you compare these two equations, you see that this function immediately is equal to this, but I don't have a function here, and I can choose whatever value on there, but I need both of the equations to be identical because it's stem streamline, right? So since the streamline, I can immediately say, hey, these have to be 0. So how about I take this equal to 0, and I take my f of r equal to u infinite r squared over 2. Okay, so if I did this, then my stream function is actually equal to u infinite r squared over 2. So now what I have found in my problem, I found what my psi is. So in this particular problem, I said my psi is going to be a function of xr in the most general sense and phi, right, in your problem. And in this problem, you can see that this is actually strictly a function of r only. I also found the potential of my function, my velocity potential, and my velocity potential in this problem was actually given by it happens to be only strictly a function of x. Okay, so this is what my stream, one of my streamlines, right, that was psi 1, and this is the velocity potential. Streamline function, velocity potential. Okay? So there are a couple of more examples that I want to discuss here before I let you go today. But there are some neat, uh, neat applications to this, and I want you to consider the following application. So here, in this case, let's consider what happened to effective gravity. This is a Freud number that we talked at the beginning of the classes, and I wanted to consider a submarine that's submerged, that's immersed in the sea, and the fluid of the extent is infinite. So all the fluid here is a big fluid and is infinite. Okay, so you can see what happens when a submarine is stationary, right? It's static, it's not moving, it's not doing anything. In this particular case, you got PN, this is a hydrostatic pressure. In the air, it becomes aerostatic pressure. And this is all it's doing is sitting there. It's actually is being balanced, right? It's not going down because you have a load that's applied here, but then you have a pressure that's actually keeping it afloat. Now here in this case, now the submarine is starting to move. As soon as it starts to move, then now you're going to have a pressure that's going to start to change, and you're going to have the velocity potential that's going to change with time. Okay. So now in this particular equation, you have to know that my starting point was this. This is my moving point. So this equation had to equate to each other, right? And so I bring the constant. So what I do is I bring the constant on this side is equal to 0. I bring this on this side is 0. So 0 is equal to 0, right? So when we do that, now note in this problem, I can cancel these out because they are on the both sides of the equation. I can bring this on this side and I can keep all the constant on this side. And now this a constant minus another constant is actually equal to a new constant. So it's just a constant that I need to find. And from here, I find this is equal to this. And note that P is equal to P minus Pn. This is the hydrostatic pressure. This was the relative pressure that we measured. This is P. So this is your new equation that you have. Now note that this equation, the way we derived it, was working because we are working on the case that is submerged in sea. So in other words, you're really, the top of the sea is over here, and this is way below down here in submerged. This approach and these equations do not apply when I'm very close to the surface. Okay, when I'm moving, even if I'm moving close to the surface, then this equation that we derived and what we are doing does not apply there. Okay, just want to keep that out there. So these are some ideas on how we will actually work in the potential flow for a three-dimensional potential flow, how it will look like.